The formation density tool radiates the formation with gamma rays from this source area and measures gamma rays returning at these detectors. By introducing a known amount of radioactive energy into the formation and monitoring its loss while in transit, a good approximation of rock density can be made. Here is how the formation density tool works. Gamma rays are emitted continuously from the source. They pass through the mud cake into the rock, where they are scattered or absorbed. Some return back through the mud cake to the detectors to be counted.
In the formation density tool, source detector spacings are so close that the device evaluates the invaded zone close to the bore wall.
The loss of gamma ray energy that occurs in transit from source to detector is caused by three effects. The first is Compton scattering, which occurs when a gamma ray collides with an electron and loses some of its energy as it knocks an electron from its orbit. The second, photoelectric effect, which occurs when a gamma ray collides with an electron and loses all its energy as it knocks the electron from its orbit. The third reaction, pair production, occurs with gamma ray bombardment. However, the gamma ray source used in a formation density tool is of relatively low energy and below the threshold of pair production. Consequently, we'll ignore pair production and concentrate on the other two effects. The net effect of these two interactions is that the number of gamma rays penetrating a substance decreases as its density increases. A returning high gamma ray count indicates low density rock. A low gamma ray count indicates high density.
What is really measured by the tool, however, is electron density, characteristically denoted by rho sub E. Let's see how the conversion from measured electron density to calculated bulk density is made.
The number of protons and neutrons of an atom determines its atomic weight, A, and therefore its contribution to the density of any molecules in which it occurs. The general relationship between bulk density and electron density is as shown here. For most common elements, the conversion ratio, 2Z over A, will be approximately 1, and the electron density will read close to true bulk density. For example, limestone, or its mineral constituent, calcite, CaCO3, has a conversion ratio of 0.9991. This represents the sum of 2 times the total number of electrons in the molecule divided by the molecular weight. Water, in contrast, has a higher conversion ratio of 1.1101 because of the presence of 2 hydrogen atoms in each water molecule.
These varying values require that a formation density tool be calibrated to a standard. The industry standard in this case is pure limestone saturated with water. The tool is calibrated to read an electron density of 1.11 in water and of 2.71 in pure limestone. This represents their true density based on calculated molecular weight.
When so calibrated, measured apparent densities of different minerals will read very close to their true densities. For example, the true density of quartz, or pure sandstone, is 2.654. Apparent density measured by gamma radiation will read 2.648.
The primary use of bulk density is to determine porosity of the rock. Porosity is calculated from the measured density in this general manner. If we know the density of a rock type with no porosity, for example 2.71 for limestone, and we know the density of pure formation water, then the measured density will represent some proportion of each.
Corrections must be made for the effects of mud cake and bore wall rugosity on tool position and gamma ray absorption. This is done by evaluating the differences in response between the close-space detector, which senses primarily the bulk densities of the mud cake and bore wall irregularities, and the long-space detector, which senses both of these, plus the bulk density of the flushed formation.